Tonight, we're going to look at a world where a single trip around the sun lasts 248 Earth years, yet the sky, frost, and ice are still changing. Pluto receives so little sunlight that noon on its surface would resemble a dim terrestrial twilight. Its average temperature is close to minus 387 degrees Fahrenheit. Its atmosphere presses down with only about 100,000th of the pressure at sea level on Earth. And still, nitrogen moves from ground to air. Methane gathers on mountain summits. Winds may help arrange grains of ice into dunes. A blue haze divides itself into delicate horizontal layers more than 120 miles above the frozen landscape. One journey around the sun takes Pluto about 248 Earth years, yet its nitrogen, methane, and haze are still in motion. But how can a world with almost no air possess anything that deserves to be called weather? By the end of tonight, you're going to understand exactly how Pluto's surface builds its atmosphere, how sunlight turns simple molecules into a layered blue haze, and why this small world belongs to a much larger frontier beyond Neptune. Before we get started, if you love exploring distant worlds as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The word weather usually brings to mind fast changes. A cloud crosses a city. A front arrives from the ocean. Rain begins and stops within an afternoon. Pluto asks us to stretch that word. Some of its atmospheric processes unfold over hours or days, but the great exchange between frost and sky follows a seasonal clock longer than recorded human history. No person has watched one complete Plutonian year. No civilization equipped with telescopes has done so either. Pluto last reached the closest part of its orbit in 1989. It will not return there until the 23rd century. A northern summer that New Horizons encountered in 2015 was part of a cycle whose earlier comparable season occurred before the American Revolution. To understand the climate, scientists combine one brief spacecraft flyby, decades of stellar occultations, laboratory measurements of volatile ice, and computer models that run through centuries. That incomplete record is not a weakness to hide. It is the central condition of studying Pluto. The world changes slowly, and human observation has only just begun. Weather survives there, not because Pluto resembles Earth, but because matter still responds to energy. Sunlight reaches the ice. Molecules escape the surface. Gravity holds some of them close. Cold regions gather what warmer regions release. The sky is thin. The cycle is long. The exchange continues. The first distinction is the most important one: pressure. Near sea level on Earth, atmospheric pressure is a little more than 1 bar. Near Pluto's surface during the New Horizons encounter, it was roughly 10 microbars, with the exact value depending on the reference level used. A microbar is 1/1,000,000th of a bar. Put another way, the pressure around Pluto was on the order of 100,000 times lower than the pressure surrounding a person standing beside Earth's ocean. That thinness changes every familiar rule. Liquid water cannot remain exposed on the surface. A human visitor would not feel a steady breeze through a suit. Clouds, if the word is used at all, would not resemble the thick towers that grow in Earth's lower atmosphere. The amount of gas above each square foot of ground is small. Yet pressure does not decide by itself whether an atmosphere can move. Gas responds to differences in temperature. It flows from areas of higher pressure toward areas of lower pressure. It transports heat, vapor, and tiny particles. Even an atmosphere measured in microbars can circulate if the surface continually feeds it and sunlight keeps one region warmer than another. Pluto's atmosphere is built mostly from molecular nitrogen. the same paired nitrogen molecule that dominates Earth's air. Methane and carbon monoxide occur in much smaller amounts. The similarity in ingredients can be misleading. On Earth, nitrogen remains a gas across ordinary weather conditions. On Pluto, nitrogen lies close to the boundary between solid and gas. A slight change in surface temperature can move molecules from a frost deposit into the atmosphere or bring them back to the ground. That phase change carries energy. When solid nitrogen sublimates directly into gas, it absorbs heat. When gas condenses into frost, it releases heat. The process helps connect distant regions of the surface because nitrogen released in sunlight can cross the globe and settle where conditions are colder. This is the foundation of Plutonian weather. The atmosphere is not a permanent ocean of air sitting above an inert floor. Surface and sky are two temporary states of the same volatile inventory. A patch of ground can become part of the atmosphere. Part of the atmosphere can become a new white layer on the ground. If you stood safely above Sputnik Planitia and returned many Earth years later, the landscape's broad outline might remain familiar while the distribution of its brightest frost had changed. The shift could be thin, regional, and difficult to see. It would still record a season. Weather here is phase change, written across a world. Pluto's weather begins with the body that holds it. The dwarf planet is about 1,477 miles, or 2,377 kilometers, in diameter. That is roughly 2/3 the diameter of Earth's moon. Its mass is only about 1/6 of the moon's, and gravity at the surface is about 6% of the Earth's. A 100-pound object on Earth would press on the ground with a weight of roughly 6 pounds there, although its mass would remain unchanged. Low gravity lets an atmosphere extend far above a small surface. New Horizons detected nitrogen-rich gas to altitudes of at least 1,000 miles during its solar occultation, when the spacecraft watched sunlight pass through Pluto's atmospheric edge. The gas became progressively thinner, but it reached surprisingly far compared with the dwarf planet's 738-mile radius. Pluto's solid body is probably arranged in layers. A rocky core lies beneath a mantle rich in water ice. At the surface, water ice behaves less like a glacier and more like bedrock because the temperature is so low. It can support mountain ranges 2 or 3 kilometers high. Nitrogen, methane, and carbon monoxide ices coat or fill parts of that rigid framework, and those more volatile materials respond strongly to sunlight. The day has its own unfamiliar scale. Pluto rotates once in about 153 hours, a little more than 6 Earth days. Its largest moon, Charon, completes an orbit in the same interval. Pluto and Charon keep the same faces toward one another, so Charon hangs above one side of Pluto and never appears above the opposite side. The spin axis is tilted about 57 degrees relative to Pluto's orbital plane. The dwarf planet also rotates in the direction opposite most planets. A large tilt exposes its hemispheres to profound seasonal changes in illumination. Because each orbit lasts 248 Earth years, those seasons persist for decades, and because the orbit is strongly elliptical, they are not equal chapters of a simple calendar. Imagine a sunrise that takes part of an Earth week to complete its full cycle. The sun would remain a brilliant point rather than a broad disk, but shadows would crawl slowly across water ice mountains. A region turning toward daylight would not warm much by terrestrial standards. It might warm enough to change which nitrogen molecules remain attached to the ground. That small difference matters because Pluto operates near volatile thresholds. Its gravity is weak, its air is scarce, and its sunlight is distant. None of those facts stops the cycle. Together, they make the cycle exquisitely sensitive. The next control is distance. Pluto does not travel around the Sun on a nearly circular path. Its orbit has a pronounced oval shape, carrying it as close as about 30 astronomical units and as far as about 49.3. 1 astronomical unit is the average distance from Earth to the Sun, roughly 93 million miles. Pluto therefore moves through a radial range of almost 20 Earth-Sun distances during a single orbit. At an average distance near 39 astronomical units, sunlight is more than 1,500 times weaker than at Earth because light spreads over an area that increases with the square of distance. Near 49 astronomical units, it is weaker still. The Sun does not stop governing Pluto. Its influence arrives as a faint but persistent budget of energy. The oval orbit also changes Pluto's speed. Like every object following an elliptical path, Pluto moves faster near the Sun and more slowly when far away. The seasons linked to that motion therefore have unequal lengths. A simple division of 248 years into 4 equal parts would miss the orbital geometry that climate models need to reproduce. Pluto reached perihelion, its closest point to the Sun, in September 1989. It then began moving outward. A naive prediction might say its atmosphere should immediately shrink as the world receded. Observations did not follow that simple line. Stellar occultations indicated that atmospheric pressure rose substantially from 1988 into the early 21st century. The reason is thermal memory. Sunlight penetrates and warms layers beneath the immediate surface. Volatile deposits respond over time rather than at the exact instant of perihelion. One hemisphere may continue receiving favorable seasonal illumination even as the dwarf planet's overall distance increases. Nitrogen stored in a large basin can buffer atmospheric pressure by sublimating or condensing in response to small energy changes. On Earth, oceans delay seasonal temperatures because water stores heat. Pluto has no liquid ocean exposed to the sky, but its surface and subsurface still store energy. The comparison is limited, yet the principle of lag remains useful. Maximum response need not occur at maximum sunlight. This is why forecasts of Pluto's future atmosphere depend on albedo, thermal inertia, the depth and location of nitrogen ice, and the geometry of seasons. Models agree that pressure changes greatly over the orbit. They do not justify a precise public countdown to a complete atmospheric disappearance. Pluto is moving outward now. Its climate is not simply turning off. It is carrying heat and volatile material forward through a season that no human observer will live long enough to watch from beginning to end. Pluto's long path appears at first to create a danger that does not exist. For a part of its orbit, Pluto is closer to the Sun than Neptune. This happened from 1979 to 1999. A flat drawing can make the two orbital paths look as though they cross, suggesting that the bodies might someday meet. The solar system avoids that encounter through geometry and resonance. Pluto's orbit is tilted about 17 degrees relative to the main planetary plane. More importantly, Pluto and Neptune occupy a stable 3-to-2 resonance. For every 3 journeys Neptune completes around the Sun, Pluto completes 2. Their positions repeat in a pattern that keeps Pluto far from Neptune at the places where a diagram's lines seem to overlap. The resonance is not merely a protection for Pluto. It identifies a whole population. Other trans-Neptunian objects locked in the same 3-to-2 relationship are called Plutinos. Pluto is the largest familiar member of that resonant family, one body among many whose orbits carry a record of Neptune's gravitational influence. The planet Neptune takes about 165 Earth years to circle the Sun. Pluto needs about 248. 3 Neptune years and 2 Pluto years both approach 495 Earth years. Over that interval, their orbital arrangement returns. The match is not a perfect numerical coincidence detached from physics. Repeated gravitational interactions help maintain the resonant pattern. If you could watch from high above the solar system for half a millennium, Pluto would trace its tilted ellipse twice, while Neptune made 3 smoother circuits nearer the Sun. The two would seem to participate in a slow choreography. At no point would Pluto behave like a stray planet about to collide with its neighbor. This relationship also points toward the history of the Kuiper Belt. Planetary scientists think Neptune migrated outward early in the solar system's development. As it moved, its resonances could capture or scatter smaller bodies. The modern distribution of classical objects, resonant groups, and the scattered disk preserves clues to that migration. Pluto is therefore both a world with weather and an orbital fossil. Its frost responds to the present Sun. Its path remembers the early rearrangement of giant planets. The boundary beyond Neptune is not empty of structure. Gravity has divided it into families, lanes, and long-period routes. Pluto occupies one of the most secure. Long before anyone knew about Pluto's haze, the world existed as 2 faint marks on photographic plates. Clyde Tombaugh discovered Pluto at Lowell Observatory in Arizona on February 18, 1930. He used a blink comparator, a device that let an observer alternate rapidly between photographs of the same star field taken on different nights. Stars remained fixed. A solar system object shifted. The work demanded patience. Each plate contained many points of light. Dust, flaws, and variable stars could imitate change. Tombaugh examined paired images until one tiny point revealed a consistent motion against the background. Pluto was then about magnitude 15, far below naked eye visibility. Its discovery emerged from an imperfect prediction. Percival Lowell had searched for a distant planet X whose gravity might explain supposed irregularities in the orbits of Uranus and Neptune. Later measurements showed that Pluto was far too small to produce the proposed effect, and that the discrepancies did not require such a planet. Tombaugh's search still found a real world, just not the massive object the original calculation expected. The name came from 11-year-old Venetia Burney in Oxford, England. She suggested Pluto, the Roman god of the underworld, for a dark and distant world. The initial letters also echoed Percival Lowell's initials, although the mythological fit stood on its own. The name was adopted in 1930. For most of the 20th century, Pluto remained smaller than the details astronomers wanted to see. Even the Hubble Space Telescope could map only broad changes in brightness and color. Charon's discovery in 1978 allowed scientists to estimate Pluto's mass more accurately by watching the moon's orbit. Stellar occultations in 1988 revealed an atmosphere as Pluto passed in front of a distant star and dimmed its light gradually rather than all at once. Each method extracted a different truth from a point that no telescope could yet turn into a landscape. Motion revealed the orbit. A moon revealed the mass. Starlight bent and absorbed at the edge revealed gas. Changes in reflected light hinted that surface frost was not uniform. The progression matters because planetary science rarely begins with a complete view. It begins with indirect evidence arranged carefully enough to make a world. Pluto's weather was detected before its mountains were photographed. The atmosphere announced itself as a softened stellar shadow. The discovery of Pluto eventually changed the map that had once welcomed it. Beginning in the 1990s, astronomers found many icy bodies beyond Neptune. The first object after Pluto and Charon recognized in what became the Kuiper Belt was 1992 QB1, discovered by David Jewett and Jane Liu. More objects followed. Some occupied resonances. Some traveled on more circular classical paths. Eris, announced in 2005, was comparable to Pluto in size and slightly greater in mass. The solar system now contained either more planets than traditional lists allowed or a need for clearer categories. In 2006, the International Astronomical Union adopted a definition. A planet must orbit the Sun, be massive enough for gravity to make it nearly round, and clear the neighborhood around its orbit. A dwarf planet meets the first two conditions, but not the third, and is not a moon. Pluto became a dwarf planet and the prototype of a trans-Neptunian category. The vote changed a noun. It did not remove a mountain, thin the atmosphere, alter Charon's orbit, or stop nitrogen from crossing the boundary between frost and gas. One journey around the Sun takes Pluto about 248 Earth years. Yet its nitrogen, methane, and haze are still in motion. That anchor makes the classification dispute feel appropriately small. Taxonomy is useful because it organizes relationships. It tells us that Pluto belongs to a population rather than standing alone as the last member of an otherwise completed planetary sequence. The Kuiper Belt gives Pluto context: shared ices, resonant dynamics, binary systems, and formation histories that differ from the 8 dominant planets. The category also prevents size from becoming the only measure of interest. Pluto is less than 1/5 the mass of Earth's moon, yet its surface has glaciers, convection, possible dunes, tectonic features, and a chemically active atmosphere. Eris is more massive but more distant. Haumea rotates rapidly and has an elongated shape. Makemake retains methane ice and a moon. Arrokoth preserves a contact binary form. If a label helps you place those bodies into a physical story, it has done useful work. If it becomes a substitute for looking at the bodies themselves, it has become too important. Pluto did not become less complex in 2006. Human knowledge became more crowded. The old edge of the planetary system opened into a broad third zone filled with worlds. The next transformation required a spacecraft. New Horizons launched from Cape Canaveral on January 19, 2006, aboard an Atlas V rocket. It left Earth faster than any previous spacecraft had been launched on an escape trajectory. A Jupiter gravity assist in February 2007 increased its speed and shortened the travel time to Pluto by several years. The probe was compact, with a launch mass of about 1,054 pounds, or 478 kilograms. It carried 7 scientific instruments. Lori provided high-resolution black and white images. Ralph mapped color and composition in visible and infrared light. Alice studied ultraviolet light and the atmosphere. Rex used radio signals to probe atmospheric structure and surface properties. Swap and Pepsi measured charged particles. A student-built dust counter recorded tiny impacts along the path. Power came from a radioisotope thermoelectric generator. At Pluto, sunlight was far too weak for a practical set of solar panels on a small, fast spacecraft. Heat from the decay of plutonium-238 produced electricity, supplying only about 200 watts during the encounter. That is comparable to a few household light bulbs divided among instruments, computers, heaters, and communications. The flyby could not be steered moment by moment from Earth. In July 2015, a radio signal needed about 4 hours and 25 minutes to cross the distance one way. By the time controllers saw a problem, the crucial geometry would already have passed. The encounter sequence was programmed in advance and rehearsed repeatedly. On July 14th, New Horizons flew about 7,800 miles, or 12,500 kilometers, above Pluto's surface at closest approach. During the busiest period, its antenna pointed away from Earth so the instruments could face Pluto, Charon, the smaller moons, and the escaping atmosphere. Controllers waited through a planned silence. A short status message arrived later to confirm that the spacecraft had completed the encounter. The probe gathered far more information than it could transmit quickly. The complete Pluto-Charon dataset amounted to about 6.25 gigabytes, modest by modern storage standards, but enormous across a link of roughly 1 or 2 kilobits per second. Returning it took more than 15 months. A person could copy that quantity of data between two nearby devices in seconds. New Horizons sent it across billions of miles, packet by packet, while continuing outward. The slow download turned one morning in 2015 into a sequence of discoveries lasting years. The first resolved portrait overturned nearly every simple expectation. Pluto was not a uniformly cratered ice ball. The encounter hemisphere contained dark equatorial terrain, bright polar frost, rugged water ice mountains, long faults, pitted plains, and a vast heart-shaped region later named Tumbo Regio. Its western lobe, Sputnik Planitia, appeared as a pale basin with broad areas almost free of impact craters. Crater density is a clock with qualifications. A surface exposed for billions of years accumulates more impact scars than a surface recently renewed, provided the impact population is understood. Sputnik Planetia's scarcity of visible craters showed that part of Pluto had been resurfaced in geologically recent time. The process was not an ancient event preserved without change. Nitrogen-rich ice was still capable of moving. New Horizons achieved its sharpest views along selected strips rather than photographing the entire world at one uniform resolution. The highest resolution mosaic crossed hummocky uplands, washboard ridges, angular mountains, cellular plains, pits, and thin deposits draped across older topography. Other regions were seen at lower resolution. Much of the far side remained known through approach images, departure views, and indirect mapping. This limit matters whenever a phrase such as Pluto has is used. It can mean a feature was observed directly on the encounter hemisphere. It can mean spectroscopy detected a material over a broader region. It can mean a model produces a global circulation consistent with the visible evidence. Those are different levels of knowledge. New Horizons also collected a snapshot rather than a long weather movie. It passed the system at more than 30,000 miles per hour. It could compare frames taken during approach and departure, but it did not remain in orbit to watch frost migrate through years or haze evolve through seasons. Ground-based telescopes and stellar occultations provide the continuing timeline, with far less spatial detail. The single flyby nevertheless connected scales that had been separate. Telescopes had measured changing brightness. Occultations had revealed a thin atmosphere. New Horizons placed those facts above mountains, glaciers, and volatile plains. It showed where some atmospheric nitrogen could be stored and what sunlight had sculpted below the haze. You can think of the encounter as one brilliantly detailed page removed from a very long climate diary. The page contains enough structure to reconstruct earlier entries and propose later ones. It does not contain the whole book. Pluto's lower atmosphere is chemically simple and physically subtle. Molecular nitrogen makes up the great majority. Methane accounts for roughly 0.5% in a commonly cited near-surface summary, and carbon monoxide for a smaller fraction. Trace hydrocarbons and nitriles form through chemistry higher in the atmosphere. The exact mixture varies with altitude and location because gases, frosts, sunlight, and escape do not affect every molecule equally. On Earth, air becomes colder through much of the troposphere, the layer where ordinary weather occurs. Pluto's atmosphere does not reproduce that familiar profile. Near the surface, New Horizons radio measurements indicated a shallow boundary layer. Above it, methane absorbs sunlight and helps warm the atmosphere, producing temperatures far above the frozen ground, even though they remain extremely cold in human terms. Pressure near the surface was around 10 microbars during the 2015 encounter. A column of gas so slight might seem incapable of obscuring anything. Viewed toward the sun, however, the path through the atmospheric limb becomes very long. Molecules and haze particles accumulate along that slant line of sight. The departing spacecraft saw Pluto ringed by a luminous blue arc. The atmosphere also extends to a large fraction of the world's size. Alice, the ultraviolet spectrograph, watched the sun disappear behind Pluto and measured how different wavelengths were absorbed. Nitrogen-rich gas was detected far above the surface. Methane becomes relatively more important at greater altitudes because molecular weight, temperature, and escape sort the upper atmosphere. The low gravity that allows this extension also permits gas to escape into space. Before 2015, several models expected a rapidly escaping comet-like outflow. New Horizons found a colder and more compact upper atmosphere, reducing estimated nitrogen escape by orders of magnitude compared with many pre-encounter predictions. This correction illustrates the value of direct measurement. The ingredients had been known. The pressure had been constrained. Yet the upper temperature structure changed the escape calculation. A small adjustment in temperature can determine whether molecules remain bound or pass beyond the gravitational boundary. Pluto's atmosphere is therefore both more extended and less freely escaping than some earlier pictures suggested. It reaches high, but it does not simply pour away. Beneath it lies a reservoir of the same nitrogen in solid form, waiting for sunlight to move the boundary again. The engine of the climate is a change of state. At Pluto's surface pressure, nitrogen does not need to melt before it enters the air. It sublimates. Molecules leave the solid directly and become gas. In a colder place, gas molecules strike the ground and remain as frost. Methane and carbon monoxide participate in related exchanges, each with its own vapor pressure and interaction with nitrogen ice. Vapor pressure is the bridge between temperature and atmosphere. For a volatile solid in equilibrium with its vapor, a small rise in temperature can produce a large rise in the amount of gas above it. Pluto's surface temperatures sit in a range where nitrogen's response is especially consequential. A difference of a few degrees can alter atmospheric pressure across the whole world. The latent heat involved resists abrupt local temperature changes. Sublimation consumes energy and cools the source. Condensation releases energy and warms the destination. If sunlight favors one nitrogen deposit, molecules rise from it, flow through the atmosphere, and settle elsewhere. The atmosphere distributes both mass and heat. Sputnik Planitia is central because it contains an enormous reservoir of nitrogen-rich ice. Its low elevation also matters. Atmospheric pressure is slightly greater in a deep basin than on surrounding uplands, and the condensation temperature changes with pressure. Topography can therefore guide where volatiles accumulate over long intervals. The process creates a climate without liquid. There is no water cycle of evaporation, cloud droplets, rain, rivers, and ocean. There's a nitrogen cycle connecting frost, gas, and flowing solid ice. Methane can gather as frost and perhaps as mobile grains. Carbon monoxide can dissolve within nitrogen-rich deposits and enter the atmosphere. If you followed a single nitrogen molecule, its history might cross several domains. It could remain locked in Sputnik Planitia for years, sublimate during favorable illumination, travel through the thin atmosphere, condense on a colder slope, return to gas in another season, and eventually settle again in the basin. A tiny fraction might reach the upper atmosphere and escape. No one can trace one molecule through that entire itinerary. Spectra reveal composition. Images reveal deposits. Occultations reveal pressure. Models connect them through conservation of energy and mass. The result is not metaphorical weather. Gas moves, frost forms, surface material migrates. The timescale and pressure are foreign, but the physics is direct. The historical pressure record contains a quiet surprise. Pluto's atmosphere was first detected during a stellar occultation in 1988. As Pluto passed in front of a star, the starlight faded gradually, bent and absorbed by gas around the limb. Similar events in 2002 showed a stronger atmospheric signature. Analyses indicated that pressure had roughly doubled over the intervening 14 years, even though Pluto had passed perihelion in 1989 and was moving away from the Sun. Later occultations continued the record. They did not all sample identical chords or use identical instruments, so interpreting the lower atmosphere requires care. The broad conclusion remained that Pluto's pressure did not respond instantly to solar distance. One journey around the Sun takes Pluto about 248 Earth years, yet its nitrogen, methane, and haze are still in motion. Climate models reproduce delayed pressure peaks when they include thermal inertia and a substantial nitrogen reservoir. The surface below the uppermost skin stores heat received earlier. Northern regions can remain strongly illuminated because of Pluto's tilt. Sputnik Planitia can supply nitrogen gas even while the average solar energy declines. Different assumptions produce different futures. A bright nitrogen surface reflects more sunlight than a dark one. High thermal inertia carries more warmth between seasons. Deep permanent ice deposits buffer the atmosphere differently from thin seasonal caps. The distribution of nitrogen on the unseen or poorly mapped side introduces further uncertainty. NASA summaries sometimes describe Pluto's atmosphere as expanding near the Sun and collapsing or freezing onto the surface farther away. That captures the governing phase change, but it should not be read as a precise forecast that the atmosphere becomes exactly zero at a known date. Some model cases preserve a global atmosphere throughout the orbit. Others allow pressure to fall by large factors. Future occultations will discriminate among those cases. A distant star will again pass behind Pluto. The shape of its fading and reappearance will reveal pressure and temperature at particular altitudes. Many such narrow measurements, collected across years, can test a climate cycle 248 years long. This is a form of scientific patience built into the subject. Researchers publish forecasts that may be checked by colleagues not yet born when the earliest data were taken. The atmosphere carries a memory of sunlight. The observing program must carry a memory of measurements. The largest visible reservoir lies inside Pluto's heart. Tumba Regio spans a broad, bright area on the encounter hemisphere. Its western lobe is Sputnik Planitia, a basin roughly 600 miles or 1,000 kilometers wide. The floor lies several kilometers below surrounding terrain and is filled with a deep sheet dominated by nitrogen ice, with carbon monoxide and methane mixed through parts of it. The basin may be an ancient impact scar, although details of its origin and later evolution continue to be studied. Its present role is clearer. Low elevation, bright volatile ice, and enormous capacity make it a long-lived cold trap and climate reservoir. Sputnik Planitia does not resemble a frozen terrestrial sea. Nitrogen ice at about 38 kelvins has mechanical properties unlike water ice on Earth. It can deform slowly under its own weight. The plane is divided into polygonal cells, often tens of kilometers across. Dark material collects in some boundaries. Pits and streaks interrupt other regions. Glaciers enter from surrounding uplands. The basin also affects the atmosphere above it. High-resolution climate simulations predict winds that follow its topography, including a western boundary current in the near-surface air. Condensation and sublimation flows driven by the nitrogen reservoir can dominate global circulation. Dark streaks observed near some margins are consistent with transport. Though a model match is not a wind gauge placed on the surface, the geography creates feedback. Bright frost reflects sunlight and remains cooler, encouraging volatile stability. Dark contamination absorbs more light and promotes sublimation. Sublimation can expose or concentrate darker material, while condensation can cover it with fresh ice. Small color differences may guide later changes. If the entire atmosphere contains only a slight fraction of the accessible surface nitrogen, then moving frost does not require creating or destroying much material. The basin supplies gas. The sky redistributes it. Cold terrain receives it. Over longer cycles, much of it may return to Sputnik Planitia. The heart shape is an accident of viewing and boundaries. The climatic role is physical. A deep depression holds the softest abundant ice on Pluto, and that ice communicates with the atmosphere every time energy shifts the balance between solid and gas. Pluto's weather has a center of gravity. It is a pale plain surrounded by mountains. Sputnik Planitia's cellular pattern reveals motion beneath a surface that appears still. Many polygons measure about 10 to 30 miles, or 16 to 48 kilometers across. Their centers tend to be slightly raised and their margins lower. Numerical models combined with topography and composition indicate slow thermal convection within a layer of nitrogen-dominated ice. Heat escapes from Pluto's interior, supplied largely by the decay of radioactive elements in rock. The flow is modest, but nitrogen ice is weak enough at these temperatures for the heat to matter. Warmer ice at depth becomes buoyant and rises. Near the surface, it cools, spreads, and eventually sinks along cell boundaries. The comparison to a lava lamp is helpful only if the speed is removed. A decorative lamp turns visibly within minutes. A convecting cell on Pluto may take hundreds of thousands of years to renew. The solid remains solid. It deforms through slow creep rather than splashing as a liquid. Crater counts and convection modeling suggest that the visible surface of much of Sputnik Planitia is less than about 1 million years old. That age is extremely young beside Pluto's 4.5 billion year history. It does not mean the basin or all its ice formed recently. It means older surface patterns have been recycled or erased. Convection also explains why polygon centers and edges differ in texture. Material rising at the center travels outward. Haze particles falling from the atmosphere can accumulate and then be swept toward margins. Pits may form where nitrogen sublimates. Some dark streaks could be influenced by winds above the ice. From an altitude, you would see a geometric plane that resembles a mosaic. Up close, each cell would extend farther than a large city. The height differences would be gentle. Motion would be invisible during a visit, yet the absence of old craters would testify to it. This slow churning connects interior geology to weather. Internal heat shapes the nitrogen reservoir. The reservoir controls atmospheric pressure. The atmosphere moves frost and haze back onto the surface. A process deep below the plane therefore influences a sky only microbars thick. Pluto is small enough to be called a dwarf planet and active enough to make that word feel merely administrative. The landscape depends on a reversal of familiar materials. On Earth, water ice flows through glaciers, while solid nitrogen exists only under laboratory or industrial conditions. On Pluto, water ice is the strong foundation. Nitrogen ice is the mobile glacier. Mountains along Sputnik Planitia rise roughly 2 to 3 kilometers. Blocks of water ice can support that relief because water is extremely rigid near minus 380 degrees Fahrenheit. Some blocks appear jumbled at the basin margin, as though they broke from surrounding crust and were carried or rotated by softer material. Nitrogen ice fills valleys and spills from uplands toward Sputnik Planitia. New Horizons images show patterns resembling terrestrial glacial flow, lobate margins, channels, and streams entering a larger sheet. The resemblance is mechanical, not climatic. Pluto's glaciers are not compressed snowfall made from water. They are volatile nitrogen moving across a bedrock of frozen water. Methane ice adds another layer. It coats broad regions, strengthens some terrains, and gathers in distinctive deposits. Carbon monoxide concentrates in parts of Sputnik Planitia. Spectral maps separate these materials by the wavelengths they absorb, allowing scientists to read composition from reflected sunlight. The layers do not always form clean geological stacks. Nitrogen and carbon monoxide can mix. Methane can be diluted within nitrogen or occur as methane-rich ice. Haze particles settle over them, adding reddish-brown organic material. Seasonal frost can cover an older surface and later retreat. Imagine crossing from a dark equatorial plain toward the Bright Basin. The ground beneath every step would be water ice, but its visible coat could change from methane-rich crust to a thin nitrogen veneer and then to the deep mobile reservoir. A water ice mountain might rise like a rocky island above the nitrogen plain. The analogy has limits. No suited traveler could safely walk across a surface near 38 kelvins with microbar pressure, and the mechanical strength of each deposit would vary. Yet the inversion remains useful. The substance that fills Earth's oceans becomes Pluto's bedrock. A gas that fills most of Earth's sky becomes Pluto's glacier. Weather moves the glacier's molecules into the air. Geology gives them a basin to return to. Away from the smoothest plain, Pluto displays terrains shaped by removal as well as deposition. Some nitrogen-rich areas are coarsely pitted. Sunlight can drive sublimation, allowing solid ice to vanish directly into gas and leaving depressions behind. The pits may grow, merge, or expose material with a different color and composition. Their shapes preserve the direction of energy flow from surface to atmosphere. Venera Terra contains fretted terrain, bright polygonal blocks separated by connected dark valleys a few kilometers wide. Fracturing probably opened the network. Nitrogen glacial movement, volatile loss at the margins, or both may have widened it. New Horizons composition maps show methane-rich ice across many of the bright blocks. Tartarus Dorsa presents another pattern, fields of tall parallel blades made largely of methane ice. The ridges resemble penitentes, the sun-sculpted snow and ice forms found in high dry regions on Earth, but Pluto's examples are far larger. Modeling suggests repeated sublimation under long-term climate conditions can carve the blades. Long troughs elsewhere reach hundreds of miles. Faults and scarps imply that Pluto's crust expanded or shifted. Some broad constructs have been proposed as cryovolcanoes, built by material erupting from the interior, though their origins remain interpretations rather than witnessed eruptions. The surface combines atmospheric erosion with tectonic history. Cratered regions place old ground beside young ground. Cthulhu Macula, the dark band west of Sputnik Planitia, contains ancient terrain colored by complex organic material. Haze particles settling from above may contribute to that reddish darkness over long periods. Nearby bright deposits show how volatile frost can hide older material. Pluto therefore offers no single surface age and no uniform weathering process. Some ground preserves impacts from early solar system history. Some is renewed by convection. Some is cut by sublimation. Some receives frost or falling haze. If you viewed the dwarf planet only in natural color from far away, broad red, white, and tan regions would dominate. At closer range, each color divides into textures. The textures reveal which material stayed, which flowed, and which became sky. One of Pluto's clearest weather signatures sits on mountain summits. Bright methane-rich frost covers ridges in parts of the dark equatorial region called Cthulhu Macula, including Pigafetta and Elcano Montes. Their appearance invites a terrestrial comparison to snow-capped mountains. The formation process appears to run in the opposite direction from familiar mountain snow. On Earth, rising air expands and cools. Water vapor condenses more readily at altitude, producing clouds and precipitation. Pluto's atmosphere is too thin and thermally structured differently. Climate simulations indicate that methane can become more concentrated several kilometers above the plains. Circulation then favors direct condensation of methane onto cold, high terrain. The deposit is frost, meaning gas becomes solid on a surface. It is not necessarily snow made of crystals that grow while suspended and then fall. That distinction resolves the most tempting image. Pluto can have white mountain tops without an Earth-like snowstorm. Topography changes the path of the air. The distribution of methane changes how sunlight is absorbed. Surface brightness changes temperature. These effects allow a narrow layer of the atmosphere to place material selectively on summits even near the equator. The same models help explain other methane reservoirs and the long blades of Tartarus dorsa. Over many seasonal and astronomical cycles, methane migrates between deposits. A summit coating visible in 2015 records both the present circulation and a history of earlier climates. Direct observation provides composition and location. Modeling supplies the mechanism. That division should remain clear. New Horizons did not film frost appearing. It measured methane-rich ice on the high ridges and atmospheric properties during a flyby. Researchers then tested whether a climate model could create the observed pattern. The result is a weather process inferred from a landscape. A bright cap becomes evidence for invisible circulation. On Pluto, a mountain need not reach into a wetter, colder troposphere. It reaches into a layer where methane is more available to condense. The air is slight, the accumulation slow, and the summit still gathers a season from the sky. Near the western margin of Sputnik Planitia, New Horizons photographed long, evenly spaced ridges. Their regular pattern resembles dunes. Composition measurements and local geology suggest that the mobile grains could be methane ice, each perhaps comparable in size to coarse terrestrial sand. The nearby Ai Idrisi Montes provide a possible source, while winds crossing the basin provide a possible organizing force. Pluto's air is too thin for ordinary wind to lift resting grains easily. Sublimation may solve the first step. As nitrogen ice turns to gas at the surface, the upward flow can loosen or loft methane particles. Once the grains are moving, even a slight wind can make them bounce, roll, and collect into ridges. Researchers estimate that the visible pattern may be geologically young, perhaps formed within the last hundreds of thousands of years, and possibly much more recently. The exact age is not measured by a calendar. It comes from the ridges crossing a surface with limited impact and disturbance. The interpretation remains open to alternatives. Repeating ridges can also emerge through sublimation erosion, where volatile loss carves the surface rather than wind building a pile. Both processes may contribute. The safe conclusion is that the pattern records active exchange among ice, gas, and terrain. One journey around the Sun takes Pluto about 248 Earth years, yet its nitrogen, methane, and haze are still in motion. A single Pluto day lasts about 6.5 Earth days. During that slow cycle, the angle of sunlight changes over the basin. Surface temperature follows with a delay. Nitrogen sublimates from favored patches. Modeled winds respond to the pressure differences. Any loose grains experience the combined effect. If you watched one ridge for an hour, nothing might move enough to see. If you compared precise images separated by decades, a measurable change might appear. New Horizons cannot provide that second close view. A future orbiter or flyby would be needed to turn the static dune interpretation into a motion record. Until then, the ridges remain one of the strongest visual arguments that microbar air can shape ground. Their existence does not require a gale. It requires enough repeated motion, enough loose ice, and enough time. On Pluto, time is the abundant ingredient. The atmosphere's small mass occupies a surprisingly deep volume. During departure, New Horizons moved behind Pluto as seen from the Sun and Earth. The ALICE ultraviolet instrument observed the solar occultation, while the REX radio experiment measured how a signal from Earth bent through the atmosphere. Together, they probed composition, pressure, and temperature across different altitudes. Near the ground, REX detected a shallow boundary layer only a few kilometers thick in at least one sampled region. Above it, atmospheric temperature rose sharply before changing more gradually. Methane's absorption of solar energy contributes to this inversion. Higher still, the upper atmosphere was colder than many pre-Flyby models had assumed. Nitrogen absorption was measured far above the surface, with the atmosphere detected out to at least about 1,000 miles in early mission reporting. That does not mean the gas formed a sharp shell ending at that altitude. Density declines continuously. At some point, individual molecules travel so far between collisions that the behavior changes from an ordinary fluid toward ballistic motion. Scale height describes how quickly pressure falls with altitude. On Pluto, low gravity and atmospheric temperature produce scale heights of tens of kilometers, varying by layer. Earth's denser atmosphere is held by stronger gravity, yet its familiar weather is concentrated much closer to the surface, relative to the planet's radius. From the ground, Pluto's sky would not necessarily look richly blue overhead. The famous blue color is strongest when sunlight travels a long slant path through haze around the limb. Looking upward through a shorter column under faint illumination could produce a dark sky with a subtle haze contribution. No camera has stood there to record the human eye view. The distinction between extent and density is essential. A wisp of gas can stretch far while containing little mass. A luminous limb can appear bright because geometry stacks many particles along the line of sight. Pluto's atmosphere is like a large transparent architecture built from sparse material. Its height shapes escape and photochemistry. Its lowest layers communicate with frost. Its visible edge emerges only when the sun shines through thousands of miles of curved path. The blue color begins with molecules that are not blue. Ultraviolet sunlight reaches Pluto's upper atmosphere and breaks apart methane and nitrogen. The fragments react, forming increasingly complex hydrocarbons and nitrogen-bearing molecules. Ions help build larger structures. Eventually, the products gather into tiny aerosol particles, often grouped under the name tholins. The individual particles are thought to be gray or reddish. Their small size lets them scatter shorter blue wavelengths efficiently when seen in the right geometry. The same broad optical principle gives Earth a blue sky, although Earth's main scatterers are much smaller in nitrogen and oxygen molecules, and its atmosphere is far denser. As haze particles settle, chemistry and condensation can coat or transform them. Models indicate that organic ice can become a major component. When the particles reach the ground, they add complex carbon-rich material to the surface. Over long periods, that deposition may help color dark equatorial regions. The haze therefore joins atmosphere and geology. Methane leaves surface reservoirs or remains in the gas. Sunlight changes it high above the ground. The resulting particles descend and become part of the landscape. A molecule can move from ice to air to photochemical smog to reddish surface coating. New Horizons photographed the haze in approximate true color after closest approach. Pluto appeared as a dark crescent surrounded by a thin blue line. The view required backlighting. From the dayside approach, the same layers were much harder to see. This geometry explains why a world can hide its most delicate feature until the spacecraft has already passed it. Forward scattered sunlight makes tiny particles bright. Mountains at the limb cast narrow shadows through the haze, producing crepuscular rays that extend outward like dark fingers. If you reduced Pluto to a simple frozen sphere, the haze would be the first correction. It shows that sunlight is still doing chemistry at nearly 5.9 billion kilometers on average from the sun. The energy is weak, but the molecules are exposed for years. Blue is not evidence of oxygen, water clouds, or a familiar atmosphere. It is the color of small particles revealing distant photochemistry. The haze is not one uniform veil. New Horizons images resolved more than a dozen horizontal layers, with some analyses identifying as many as about 20. They extend around the limb for hundreds of miles and rise above 120 miles, or 200 kilometers. The spacing is irregular, and the layers vary in brightness. Layering can arise when atmospheric waves organize particles into bands of higher and lower concentration. Air flowing over mountains may generate gravity waves, not gravitational radiation, but oscillations in a stratified atmosphere, restored by buoyancy. Temperature variations can change where vapors condense onto haze. Tides connected to Charon and daily heating may also influence structure. No single explanation needs to create every band. The atmosphere contains several interacting rhythms. Pluto's 153-hour rotation, Charon's matching orbital period, local topography, seasonal circulation, and waves traveling vertically. Haze particles fall slowly through that changing environment. The layers are observed facts. Their moment-to-moment behavior is less certain. New Horizons captured them across a limited encounter, and later reprocessing extracted detail from those images. It did not remain long enough to watch a complete cycle of formation and decay. The visual delicacy can obscure the scale. A layer only a few pixels thick in a departure image may span a vertical interval measured in kilometers and wrap around a large fraction of the world. The mountains casting shadows into it are themselves 2 or 3 kilometers high. From a viewpoint behind Pluto, the sun would illuminate successive bands like the edges of nested shells. The surface below would be nearly black. A bright arc would reveal where gas and particles intercept the light. Those bands are weather records, without a weather station. Their spacing encodes atmospheric stability and wave motion. Their color encodes particle size. Their altitude encodes the reach of photochemistry. Pluto's sky is almost empty by terrestrial standards. It is not structureless. The atmosphere must circulate because its sources and sinks are uneven. Sunlit nitrogen deposits release gas. Cold regions remove it. Sputnik Planitia sits below surrounding terrain and contains the dominant visible reservoir. Pluto's tilted rotation and long season produce different energy budgets across latitude and longitude. Pressure gradients follow. Global climate simulations using New Horizons topography and ice maps predict a circulation dominated by retrograde flow through much of the atmosphere. Near the surface of Sputnik Planitia, they produce a current along the basin's western boundary. The modeled wind affects sublimation rates, heat transfer, and the movement of dark material. Observed streaks in the basin provide a comparison. Their orientation is consistent with transport by the predicted flow, but the evidence is indirect. New Horizons carried no anemometer to the ground. The wind direction and speed come from models tested against patterns, temperatures, and volatile distributions. At microbar pressure, dynamic pressure is extremely low. A wind can move quickly in meters per second, while exerting little force because so few molecules strike an object. This is why sublimation may need to loosen grains before wind can arrange them into dunes. Condensation flow can itself drive circulation. When nitrogen becomes gas in one region and frost in another, the atmosphere carries mass across the planet. The strongest motion need not resemble a terrestrial jet stream powered by equator to pole heating. It can be tied directly to the volatile reservoirs. Topography then redirects the flow. A basin wall, mountain chain, or broad slope changes pressure and channels near surface air. Methane availability changes with altitude. Haze settles through waves generated below. For a safe imagined observer, the landscape would not announce this motion with bending trees or blowing fabric. There are no plants, and the atmosphere could barely push a flag. Evidence would appear in streaks, frost boundaries, and grains shifted over long intervals. Weather does not require spectacle. It requires transport. Some atmospheric molecules never return to frost. Pluto's gravity is weak, and the upper atmosphere receives ultraviolet energy from the sun. Molecules at high altitude can gain enough energy to escape, while ionized particles interact with the solar wind. Before New Horizons, several calculations predicted a broad comet-like outflow of nitrogen. The flyby found a different regime. The upper atmosphere was colder and more compact than expected. Revised estimates placed nitrogen escape near 10 to the 25th molecules per second rather than the much larger values in many earlier models. That still represents continuous loss, but it is measured against an enormous reservoir of surface nitrogen. The solar-wind interaction was correspondingly smaller. SWAP measured how charged particles from the sun changed near Pluto. The boundary did not stand millions of miles upstream, as a huge escaping atmosphere might have produced. Methane escapes more readily relative to nitrogen at high altitude because lighter molecules separate upward. Photochemistry also consumes methane, turning part of it into haze that falls back down. The atmospheric inventory is therefore governed by several paths: condensation, sublimation, chemistry, deposition, and escape. Over the age of the solar system, even a modest leak can matter. The present escape rate cannot simply be multiplied backward 4.5 billion years because solar ultraviolet output, atmospheric temperature, volatile supply, and Pluto's orbit have changed. Researchers study possible sources and reservoirs rather than treating one snapshot as an eternal constant. Sputnik Planitia again provides scale. Its nitrogen sheet is deep and broad. A loss that sounds large when counted molecule by molecule can remain small compared with the solid reservoir. Numbers need a denominator. If you watch Pluto from the side, no visible stream would trail behind it. Escape occurs particle by particle at the edge where collisions become rare. Instruments detect it through absorption, ions, and changes in the solar wind. The weather cycle is not perfectly closed. Most nitrogen may move between surface and atmosphere. Some haze settles. Some gas departs forever. No tour of Pluto's climate can ignore the companion occupying its sky. Charon is about 750 miles, or 1,208 kilometers, in diameter, roughly half Pluto's width. Its mass is large enough that the shared center of mass lies outside Pluto's surface. Both bodies orbit that point every 6.387 Earth days, the same interval as their rotations. The mutual tidal lock creates an unusual geography. From Pluto's Charon-facing hemisphere, the moon remains in nearly the same place in the sky. From the opposite hemisphere, Charon never rises. A longitude can therefore be permanently defined by whether the companion is visible. One journey around the sun takes Pluto about 248 Earth years, yet its nitrogen, methane, and haze are still in motion. Charon's steady position does not mean its influence is absent from atmospheric rhythms. Its gravity raises a static tidal figure and may contribute to periodic effects in the atmosphere. The shared rotation also sets the 153-hour day that modulates sunlight. The two surfaces look markedly different. Charon lacks Pluto's broad reservoir of mobile nitrogen and its global haze. It displays immense canyons, smoother plains, cratered terrain, and a dark reddish polar region called Mordor Macula. Material escaping Pluto may contribute to that polar coloring after methane is captured and chemically transformed, though the full history is complex. The likely origin of the system is a giant collision early in solar system history. Debris assembled into Charon and the four smaller moons. The system became dynamically compact, with moon orbits close to a common plane. People sometimes call Pluto and Charon a double planet because their sizes are relatively similar and their barycenter lies outside Pluto. That phrase is descriptive rather than an official IAU category. Physically, it conveys the view. Not a dominant world with a tiny attendant, but a close pair turning face to face. If you stood on the near side across many Pluto days, Charon would not cross the sky. The sun and stars would move around it. Weather would alter frost below while the companion held its station above. Beyond Charon, four small moons complete the family. Nix and Hydra were discovered in Hubble Space Telescope images in 2005. Kerberos followed in 2011 and Styx in 2012. Each is irregular rather than spherical, and each measures less than about 100 miles across. Their names continue the underworld theme around Pluto and Charon. Unlike the mutually locked central pair, the small moons rotate in complicated ways. New Horizons observations showed rapid spins and unusual orientations. The changing gravitational pull of Pluto and Charon helps prevent simple tidal locking, especially for elongated bodies in the binary system's variable field. Hydra completes an orbit in roughly 38 days, while Styx, Nix, and Kerberos occupy progressively wider routes between Charon and Hydra. Their orbital periods sit near chains of integer ratios with Charon, though describing every relationship as a perfect resonance would go too far. The moons are bright, consistent with water ice-rich surfaces. Nix shows a reddish region that may mark an impact crater. Hydra reflects a large fraction of incoming light. Kerberos turned out to be smaller and brighter than some pre-flyby estimates had suggested. New Horizons had to search for hazards before closest approach, An undiscovered ring or dust cloud could have damaged the spacecraft at encounter speed. The mission team used long exposure images to examine the system and retained alternate routes, but no dangerous ring was found. Pluto has no known rings. The small moons preserve evidence for the ancient collision that formed Charon. A debris disk around the central pair could have assembled into multiple bodies. Their nearly coplanar, near-circular orbits support a shared origin, while their chaotic spins reveal the continuing dynamical complexity. These moons do not control Pluto's nitrogen cycle. Their importance is context. Weather occurs on one member of a tightly connected miniature system. Each 6-day rotation carries Pluto, Charon, and the small moons through a changing pattern of sunlight and mutual gravity. From far away, all 6 bodies once blended into a point. By 2015, they had become a system with individual shapes, colors, rotations, and histories. Pluto's wider neighborhood begins near 30 astronomical units from the Sun. The main Kuiper belt occupies a thick, donut-shaped region beyond Neptune and extends to roughly 50 astronomical units. It is not a narrow ring and not a hard-edged container. Objects move on orbits with different inclinations, eccentricities, and resonances, filling a broad three-dimensional volume. Beyond and overlapping the main belt lies the scattered disk. Its members follow more elongated and tilted paths, some reaching hundreds of astronomical units from the Sun. Detached objects such as Sedna travel on routes whose closest points remain too distant for strong present-day encounters with Neptune. Farther still, the hypothesized Oort cloud forms a separate and vastly more remote comet reservoir. Kuiper belt objects are remnants of solar system formation, but the word remnant should not imply they remained untouched. Neptune's migration scattered, captured, and reorganized many of them. Collisions broke some bodies apart. Binary pairs survived. Volatile surfaces changed under radiation and seasonal sunlight. NASA's current summary notes more than 2,000 cataloged trans-Neptunian objects, while estimates suggest hundreds of thousands wider than 100 kilometers. The known sample is shaped by telescope sensitivity. Small, dark, distant bodies are difficult to detect, and the sky coverage needed to find them is immense. The belt's total mass is thought to be no more than about a tenth of Earth's mass today. Formation models often begin with more material and remove much of it through early dynamical evolution. The surviving bodies are numerous but collectively light. If you traveled outward from Neptune, you would not see a crowded field of ice. Most objects would remain millions of miles apart. The belt is recognized statistically through orbits, not visually as a luminous band. Pluto sits inside that sparse structure as its largest known member by size. And Eris is slightly more massive. The distinction emphasizes how many measures a neighborhood can contain: width, mass, brightness, composition, and orbital family. The Kuiper belt is the edge of the classical planetary map, not the edge of the solar system. It is where the 8 planets give way to a population. The population becomes legible when its orbits are sorted. Classical Kuiper belt objects travel on relatively stable paths within the main belt. Astronomers divide them further into dynamically cold and hot populations. The temperature words describe orbital motion, not surface temperature. Cold classical objects have orbits with lower inclinations and eccentricities. Hot classical objects occupy a broader range of tilted and stretched paths. That distinction carries information about origin. The cold classical population may have formed close to where it remains, preserving binaries and surfaces that escape the strongest scattering. The dynamically hot population was more thoroughly stirred during the migration of the giant planets. Their current neighborhood contains bodies with different birthplaces mixed together. Resonant objects follow repeated ratios with Neptune. Pluto and the Plutonos occupy the 3:2 resonance. A separate group follows a 2:1 pattern farther out. Resonance does not lock an object at one fixed distance from Neptune. It controls the timing and orientation of repeated approaches so that the gravitational exchanges remain organized. Scattered disk objects carry the mark of stronger encounters. Their orbits can be elongated and steeply inclined, with closest approaches still near Neptune's realm and distant points far beyond the main belt. Neptune continues to modify many of those paths over time. Some scattered bodies may eventually move inward and become centaurs, crossing among the giant planets or be ejected outward. Detached objects add another puzzle. Sedna, for example, never approaches the Sun more closely than about 76 astronomical units and can travel to roughly 1,200. Neptune, in its present orbit, cannot easily account for that detached path by itself. Proposed influences include stellar encounters in the Sun's birth cluster, an unseen distant planet, or early configurations of the solar system. No single explanation is established for every detached object. These orbital groups overlap in physical appearance. A red surface does not automatically reveal a resonance. An icy composition does not identify a birthplace. Astronomers need years of position measurements to calculate a reliable orbit. A newly found point of light gradually becomes a member of a dynamical family. If you plotted those paths at true scale, the drawing would look less like a belt and more like transparent loops woven through a thick volume. Neptune's nearly circular route would sit near the inner edge. Pluto's tilted ellipse would cross above and below the main plane. Scattered orbits would stretch outward like narrow petals. Detached paths would begin beyond the familiar frame. The structure is a history written in motion. Present positions change every night. Orbital relationships endure for millions or billions of years. Resonant motion has another useful detail. The critical angle of the orbit does not circulate freely through every value. It librates, rocking around a preferred relationship. That oscillation keeps the longitude of close approaches away from danger. Pluto can move inside Neptune's average distance without ever sharing Neptune's immediate neighborhood. The protection emerges from repeated timing rather than a solid barrier. Surface colors cut across these dynamical categories. Cold classical objects often appear very red, while other populations contain both red and more neutral members. Radiation changes methane and other carbon-bearing ice into complex material. Collisions expose fresher layers. A color survey, therefore, adds a chemical history to the orbital one, but it does not produce a simple code in which every family receives one shade. Binary frequency adds another record. Pairs with comparable components are common in parts of the Kuiper belt. Wide, fragile binaries could not survive repeated close encounters with Neptune, so their presence among cold classical objects supports a quieter dynamical past. Pluto and Charon are a tight evolved pair, different in scale and history, but part of the same broad tendency for distant objects to keep companions. Pluto's weather belongs to the upper surface of one resonant body. Beneath that meteorology lies a clockwork relationship with Neptune. Around it lies a population whose clocks run on many other ratios. The frontier is not disorder. It is order that took decades of observation to see. The next fact is emptiness. Science fiction images often turn asteroid belts into obstacle courses and distant icy belts into fields of tumbling boulders. The real Kuiper belt occupies such an enormous volume that its members are separated by vast distances. Hundreds of thousands of large bodies can inhabit it without creating a crowded view from any one of them. Pluto's nearest companions in an illustration are not necessarily nearby in space. A diagram compresses billions of miles until orbital lines can fit on a page. It enlarges each world millions of times so a viewer can see it. Remove those adjustments and almost every object disappears. The inner edge near 30 astronomical units is about 2.8 billion miles from the Sun. The main region's outer boundary, near 50 astronomical units, lies about 4.6 billion miles away. The volume between them is thick as well as wide. Even the largest bodies occupy an almost negligible fraction. This sparse arrangement explains why New Horizons did not simply choose another target after Pluto from a dense nearby field. Mission planners needed telescopes, including Hubble, to search a narrow reachable region along the spacecraft's trajectory. Arrokoth was found in 2014, years after launch, as a faint object positioned so that the remaining fuel could guide New Horizons past it. Dust exists in the region, and the student dust counter has measured grains along the journey. Yet the probability of striking a dangerous macroscopic object is tiny. The greater challenge is locating a scientifically useful body close enough to the spacecraft's path. Emptiness also affects collisions. Impacts happen over geological time, not because objects continually brush past one another. Early in solar system history, the Kuiper belt likely held far more mass, and collision rates were higher. Today's surfaces preserve both that busier past and the slower accumulation of later craters. For a traveler leaving Pluto, the dwarf planet would shrink before another known world grew large. Charon and the small moons would remain the only nearby landmarks. The sun would look like an intense star. Other Kuiper belt objects would blend with background points unless navigation already provided their positions. The silence between bodies is part of the belt's identity. It permits fragile binary systems to survive in some populations. It makes discovery dependent on precise motion against dense star fields. It turns each close spacecraft encounter into a rare event. A survey discovers that motion by returning to the same field again and again. Software aligns the stars, measures every faint source, and searches for a point that shifts at the slow rate expected beyond Neptune. The farther the body, the smaller its apparent movement over one night. Observers then revisit it across months and years. A short observational arc can fit several possible orbits, while a long arc reveals whether the object is classical, resonant, scattered, or detached. Brightness introduces another uncertainty. A small reflective body and a larger dark body can send the same amount of light to a telescope. Infrared measurements of thermal emission help separate size from albedo, and stellar occultations can trace a silhouette directly when geometry happens to align. This is why the census is not simply a list of dots. Every entry requires a chain of inference. Even the estimate of hundreds of thousands larger than 100 kilometers is statistical. Surveys sample limited regions and detection depths, then correct for what their cadence and sensitivity would miss. The belt's emptiness makes individual encounters rare, while its enormous volume allows the unseen population to remain large. There is comfort in the scale if it is stated plainly. The edge of the solar system is not packed with hazards. It is mostly distance. Pluto occupies a small island of geology and weather inside an ocean measured in astronomical units. Pluto is the most familiar Kuiper belt world, but it is not the only one large enough to become round. Eris travels in the scattered disk on a much more distant and elongated orbit. It is close to Pluto in diameter and slightly more massive. The discovery of Eris forced the classification question, because a solar system containing Pluto as a planet had a strong reason to include Eris as well. Eris has a small moon named Dysnomia. Haumea is different in nearly every visible way. It rotates in under 4 hours, so rapidly that its figure is stretched into an ellipsoid rather than a simple sphere. It has 2 moons and a ring. a family of smaller objects shares similar water ice signatures and related orbits, consistent with fragments from a major ancient collision. Makemake is bright, methane-bearing, and accompanied by a small moon. Its atmosphere, if present now, is far less substantial than Pluto's global atmosphere observed in 2015. Seasonal or localized gases may still occur, but the evidence and volatile inventory differ. Quaoar, Gong, Orcus, and other large trans-Neptunian bodies extend the catalog. Some have moons. Some show water ice, methane, or complex reddish material. Their names come from many cultural traditions rather than one underworld theme. Comparing them reveals why Pluto's weather cannot be assigned to size alone. A body must retain volatile compounds. Its surface temperature must place those compounds near useful phase boundaries. Gravity must hold enough gas. Its orbit, tilt, albedo, and ice distribution must create transport. Pluto happens to combine these conditions with a large nitrogen reservoir visible at Sputnik Planitia. Triton, Neptune's largest moon, provides a related comparison even though it is not a Kuiper Belt object today. Its retrograde orbit suggests it was captured, probably from the trans-Neptunian population. Voyager 2 saw nitrogen frost, a tenuous atmosphere, and active plumes there in 1989. Pluto and Triton may represent different outcomes for related icy building materials, one remaining in solar orbit and one captured by a giant planet. The names can create an impression of a completed census. It is not complete. Detection favors larger, brighter, and nearer bodies. A dark object at a distant point in an elongated orbit may remain unknown. Orbital surveys continue to add smaller members and refine the paths of known ones. If you arrange these worlds side by side, physical variety would replace the old image of identical leftovers. Pluto would show its bright heart and layered haze. Haumea would appear elongated. Arrokoth would form two joined lobes. Eris would reflect distant sunlight from a colder orbit. Their differences would be as important as their shared location. The Kuiper Belt is not a shelf of unused pieces. It is a museum of early materials altered by 4.5 billion years of collisions, radiation, rotation, and seasons. Moons and rings widen the comparisons. A moon's orbit reveals the mass of its primary. Mutual events, when one body crosses another, reveal size and shape. Haumea's ring shows that ring systems are not restricted to giant planets. Quaoar has a ring lying unusually far from the body relative to the classical Roche limit expectation. Each result forces a rule learned near the planets to be tested under a new combination of gravity and ice. Volatile retention creates another sequence. Pluto holds a global nitrogen atmosphere at least during the observed season. Eris can carry bright volatile frost across a colder orbit. Makemake shows methane, but no Pluto-like global pressure has been established. Smaller or warmer bodies lose the most volatile compounds more readily. Gravity, temperature, and history combine, so there is no single diameter at which weather begins. That diversity is why close exploration of one body cannot stand in for all the others. New Horizons transformed Pluto and Arrokoth in opposite ways. Pluto became more active and layered than its point of light suggested. Arrokoth became more primordial and gently assembled. The next close target would almost certainly break another convenient generalization. New Horizons continued outward after the Pluto encounter. On January 1, 2019, it flew past a small Kuiper Belt object, then known by the designation 2014 MU69 and later named Arrokoth. The encounter occurred about 1 billion miles beyond Pluto and became the most distant close exploration of any object. Arrokoth is roughly 22 miles or 36 kilometers long and consists of two flattened lobes joined at a narrow neck. It is a contact binary. The larger and smaller components once orbited one another separately before coming together at a low enough speed to remain joined rather than shatter. Early images made the object look like a round-bodied snowman. Departure geometry and later analysis revealed that both lobes are flattened, more like two uneven pancakes joined edge to edge. The correction is another reminder that a single viewing angle can conceal three-dimensional form. Arrokoth's surface is reddish, likely colored by complex organic material produced as simple ices were irradiated over time. Craters and bright patches appear across it, but the body lacks Pluto's gravity, roundness, mobile nitrogen glacier, and global atmosphere. It preserves an earlier scale of construction. Models of its formation favored gentle assembly within a collapsing cloud of small solids. Particles concentrated locally formed two lobes and lost orbital energy until they touched. The object does not prove that every Kuiper belt body formed in exactly that manner, but it gives direct evidence that low-speed accretion could preserve delicate paired shapes. One journey around the Sun takes Pluto about 248 Earth years, yet its nitrogen, methane, and haze are still in motion. Arrokoth's year is longer still, but its weather is effectively absent. The comparison shows that distance alone does not create atmospheric activity. Pluto's larger mass, volatile inventory, and reservoir geometry make the difference. Two bodies can inhabit the same frontier and occupy entirely different levels of planetary behavior. During the flyby, New Horizons again operated from stored commands. Radio signals took more than 6 hours to travel one way. The spacecraft passed within a few thousand kilometers and returned detailed images over many months. Its remaining power and fuel have continued to support observations of the distant environment and remote Kuiper belt objects. The route from Pluto to Arrokoth changes the meaning of edge. Pluto once seemed like the final destination. 4 years later, it became the inner landmark on a longer road. Arrokoth then became the farthest body seen close, while the spacecraft continued beyond it. Every explored edge becomes a new reference point. The images also change the story of collision speed. The neck between the lobes appears too intact for a violent impact. Both components preserve organized shapes and surface structure. Their union is consistent with walking speed contact after gas drag, dynamical friction, or interactions within a local swarm removed orbital energy. The exact path is modeled, but the gentle final contact is written into the body that survived. Arrokoth rotates about once every 16 hours. Its small gravity cannot pull the joined form into a sphere. Escaping from the surface would require only a few meters per second, so loose material moves under conditions unlike those on Pluto. Bright material in the neck may collect where slopes and illumination favor it, though the surface remains only partly resolved. New Horizons observed Arrokoth with the same basic suite that studied Pluto, but less light, less time, and a much smaller target. Lori resolved shape and craters. Ralph measured color. The dust and plasma instruments sampled the surrounding environment. No atmosphere or moon was found. The silence around the object became a measurement too. Pluto's next chapter will be measured mostly from Earth. The dwarf planet continues outward from the sun and will reach aphelion, its farthest point in the 22nd century. Northern illumination will change. Volatile deposits will respond according to their brightness, depth, and thermal inertia. Atmospheric pressure is expected to decline at some stage, but the size and timing of that decline remain model dependent. Stellar occultations offer the most sensitive continuing measurement. When Pluto passes in front of a distant star, observatories distributed across a narrow track record the light curve. The central flash, gradual dimming, and recovery constrain atmospheric layers. Coordinated telescopes can distinguish Pluto's solid shadow from refraction through its gas. The technique depends on precise prediction. Pluto and the star appear as tiny points. The shadow path crosses only part of Earth. Clouds can remove a station at the critical moment. A successful observation may last minutes, yet it extends a climate record spanning decades. Infrared spectroscopy can monitor surface ices and atmospheric methane. High-resolution imaging can track broad albedo patterns, though no current telescope can reproduce New Horizons detail. Future large observatories may improve the maps. A dedicated Pluto orbiter would transform the subject by watching weather, geology, and moons across time. But such a mission would require a long journey and major planning commitment. The most valuable test may be simple persistence. Does pressure begin a steep fall, remain near a plateau, or decline gradually? Do broad frost signatures change as predicted? Are haze properties stable across the observable record? Each answer narrows the range of thermal inertia and volatile distribution. There is an asymmetry between model and witness. A computer can advance through several Pluto years in hours. A scientific community can observe only a fraction of one. Models must therefore be constrained by every independent kind of evidence: present ice maps, occultation pressures, surface temperatures, topography, and long-term brightness changes. Some predictions made now will be tested after their authors' careers. More distant seasonal phases will be observed by institutions and instruments that do not yet exist. The continuity belongs to archived data, calibrated methods, and clearly stated uncertainty. If you look at Pluto through a telescope tonight, no visible weather front crosses the point of light. The observation still joins a chain. Tombaugh's plates established motion. The 1988 occultation established air. New Horizons established landscape. Later occultation measure the climate's direction. The 248-year clock requires science to work across generations. Calibration is as important as persistence. An apparent pressure change can arise if different occultations probe different latitudes, if Pluto's center is placed slightly differently relative to the star, or if analyses assume different temperature profiles. Reprocessing older light curves with consistent methods lets researchers separate instrumental history from atmospheric history. Surface pressure is also not the only forecast target. Haze abundance responds to methane supply and ultraviolet chemistry. Frost maps respond to volatile transport. Broad brightness changes reveal which hemisphere presents reflective ice. A future measurement that contradicts one model may identify a missing reservoir rather than invalidate the whole phase change framework. The strongest forecast is therefore a set of conditional paths. If nitrogen remains deep and bright in Sputnik Planitia, pressure follows one curve. If substantial deposits exist elsewhere, it follows another. If thermal inertia is high, the surface releases stored heat slowly. Every new observation changes the weights among those paths. This discipline turns uncertainty into a plan. It tells astronomers what to measure next. It also protects the title from becoming a frozen claim of its own. Still Has Weather is supported by the atmosphere, haze, frost, and transport, observed or inferred in the modern era. It does not promise that every process keeps the same strength throughout the entire orbit. A climate can remain active while changing regime. Nitrogen may move from a broad global atmosphere toward more localized exchange. Haze production may respond to a changing methane supply. Frost may gather where the 2015 map showed bare ground. Continued weather can include a thinner sky. That is the experiment now underway. Pluto is moving through a part of its orbit never before observed with modern instruments. There is no older spacecraft baseline waiting at the same season. Every well-calibrated measurement is both a result and a foundation. Now the tour can move outward in one continuous line. Begin above Sputnik Planitia. The pale nitrogen plane fills the basin below. Polygonal cells rise and sink too slowly to see. Along the margins, nitrogen glaciers descend between mountains made of water ice. Methane frost brightens selected summits. Dark haze material rests where volatile cover has thinned. Rise through the first kilometers of atmosphere. Pressure falls from an already tiny value. Methane absorbs distant sunlight and changes the temperature profile. Modeled winds follow the basin and carry material across boundaries that no camera can mark. Continue above 120 miles. Horizontal haze layers circle the limb. Small particles scatter blue light toward a viewpoint behind Pluto. Ultraviolet radiation continues the chemistry that began with methane and nitrogen. Below, the particles settle toward a surface they may darken. Move beyond Charon's orbit. The large moon and Pluto revolve around an empty point between them, keeping the same faces inward. Styx, Nix, Kerberos, and Hydra trace wider paths, spinning without the central pair's composure. The whole system shrinks into the point of light it once was from Earth. Continue toward the scale of Pluto's solar orbit. The ellipse stretches from about 30 to 49.3 astronomical units and tilts across Neptune's plane. Neptune completes 3 circuits while Pluto completes 2. Their paths cross in projection, but remain safely phased in space. Pull farther back until the main Kuiper belt becomes a thick torus rather than a line. Classical objects occupy stable regions. Plutonos share Pluto's resonance. Scattered bodies travel on long tilted loops. Detached objects remain farther out. The distribution records Neptune's ancient migration. At this scale, individual worlds vanish. More than 2,000 cataloged trans-Neptunian objects become a sparse sample, and the estimated hundreds of thousands, larger than 100 kilometers, remain mostly unseen. The belt's name suggests material. The view is dominated by the gaps. Pass Arrokoth's orbit, where 2 flattened lobes preserve a gentle joining. Continue into the scattered disk, whose outer reaches approach 1,000 astronomical units. Do not confuse that region with a wall. The sun's gravitational domain and the possible Oort cloud extend vastly farther. Look back. Pluto is no longer the last world. It is one active station near the inner portion of a broad frontier. Its atmosphere is too thin to see. Its heart-shaped basin is smaller than a pixel. The weather continues without requiring an audience. This outward movement changes scale, but not the governing idea. Energy arrives. Ice responds. Gravity organizes paths. Time accumulates effects that a brief visit cannot show. The last close image is not the end of Pluto. It is the beginning of the interval we now have to infer. At Pluto's average distance, light itself needs more than 5 hours to travel from the Sun to the dwarf planet, and a similar interval to return toward an observer near Earth. The landscape seen by a telescope is already hours old. That delay is negligible beside a 248-year climate cycle, yet it offers one more measure of how far the tour has moved. The scene also has no fixed up or down. The ecliptic plane is only a reference inherited from the planet's formation. Pluto crosses it on a 17-degree tilt. Scattered objects climb much farther above it. A 3-dimensional tour would repeatedly lose the flat disk that classroom diagrams encourage. Beyond the main belt, sunlight continues weakening with the square of distance. At 100 astronomical units, it is 1/10,000th of the intensity at Earth. A volatile surface there can remain cold for centuries, while cosmic rays and ultraviolet photons slowly process its uppermost molecules. Change becomes sparse, not absent. Turn back once more toward Pluto, and the distinction becomes clear. Its weather is not produced by being at the edge. It is produced by the particular balance Pluto carries through that edge. Enough gravity, enough nitrogen, enough seasonal energy, and a basin capable of storing mobile ice. We have talked about a year that lasts 248 Earth years, and a day that lasts more than 6. We have talked about an orbit stretching from roughly 30 to 49.3 astronomical units, crossing Neptune's path only on a flat diagram, while a 3-2 resonance keeps the world safely arranged. We have talked about a surface pressure measured in microbars, an atmosphere made mostly of nitrogen, and a ground covered in compounds that can become part of that atmosphere without ever becoming liquid. We have talked about Sputnik Planitia, the 1,000-kilometer basin where nitrogen-rich ice fills an ancient depression and rises and sinks through convective cells tens of kilometers wide. We have talked about mountains made from water ice, glaciers made from nitrogen ice, methane frost placed on equatorial summits, and ridges that may be dunes moved by the combined work of sublimation and wind. We have talked about the blue line around Pluto's limb, not an Earth-like sky, but sunlight scattered by particles assembled through methane and nitrogen chemistry high above the ground. We have talked about horizontal haze layers rising beyond 200 kilometers, divided by waves and temperature structure inside air that contains very little mass. We have talked about an atmosphere that increased in pressure after perihelion because climate remembers earlier sunlight, and about forecasts that must remain conditional because no one has watched a complete Plutonian season. We have talked about Charon holding nearly the same place over one hemisphere, 4 smaller moons rotating through a changing gravitational field, and a system probably assembled after an ancient collision. We have talked about the blink comparator that revealed Pluto in 1930, the occultation that revealed its air in 1988, and the spacecraft that crossed its system in 2015 with only one chance to turn stored commands into measurements. We have talked about a classification changed by the discovery of neighboring bodies, while the physical world continued exactly as before. We have talked about the classical belt, the resonant groups, the scattered disk, and detached paths extending beyond Neptune's present reach. We have talked about Eris, Haumea, Makemake, and Arrokoth, each showing that the distant population is not a collection of interchangeable ice. And through every scale, from one haze particle to a 248-year orbit, the same pattern has remained. Pluto is cold without being inert. It is distant without being isolated from sunlight. It is small without being simple. The title began with a present tense claim. Pluto still has weather. Every part of that sentence now has a boundary. Pluto means one member of a larger population. Still means the processes were active in the evidence gathered during the modern observing era and are expected to continue. Not that a permanent atmosphere is guaranteed at every point in the orbit. Weather means gas, frost, haze, wind, transport, and change under conditions far from terrestrial experience. Those boundaries do not weaken the claim. They make it accurate. We have also talked about evidence arriving in different forms. An image gives morphology. A spectrum identifies molecules. An occultation gives a vertical pressure and temperature path. An orbit gives mass and dynamical family. A climate model tests whether the pieces can obey energy and mass conservation through seasons no one has observed. We have talked about corrections. Planet X was not the massive perturber once thought. Pluto was smaller than early estimates. Its upper atmosphere escaped more slowly than many pre-flyby models expected. Arrokoth was flatter than the first snowman-like images implied. Revision did not erase discovery. It converted a useful first picture into a better one. We have talked about scales nested inside one another. Micron-sized haze particles, kilometer-high mountains, 1,000-kilometer nitrogen basin, a binary system tens of thousands of kilometers wide, an orbit billions of miles across, and a belt extending far beyond the last planet. The assembled view is not a list of curiosities. Each scale leads to the next. Photochemistry colors the ground. Topography guides frost. Frost supplies pressure. Pressure drives circulation. Orbit controls sunlight. Neptune organized the orbit. Early solar system history organized the belt. The honest answer to the title is yes. Pluto still has weather. It has weather when sunlight lifts nitrogen molecules from Sputnik Planitia into a tenuous atmosphere. It has weather when colder terrain receives those molecules as frost. It has weather when methane becomes enriched above the plains and gathers on high ridges. It has weather when pressure differences drive mottled winds around a basin. It has weather when ultraviolet light builds haze particles and atmospheric waves arrange them into blue layers. This is not weather made small by comparison with Earth. It is a different limit of the same physics. Energy is uneven. Matter changes state. Gas moves. Gravity retains most of it. A surface records what the atmosphere has carried. The familiar signs are absent. No ocean supplies rain. No tree marks the wind. No thick cloud darkens an afternoon. A storm does not cross a continent before a forecast can be updated. Pluto's strongest climate record may be a frost boundary that shifts across decades, a pressure curve assembled from starlight, or a plain resurfaced across hundreds of thousands of years. The title's word still reaches in two directions. It points backward to the old expectation that a small frozen body so far from the sun should be geologically finished. New horizons replace that expectation with glaciers, convection, haze, and possible dunes. It also points forward because Pluto is moving away from the sun and its atmospheric future remains under observation. The sky may thin greatly, volatiles may migrate. The exact path has not yet been measured. One journey around the sun takes Pluto about 248 Earth years, yet its nitrogen, methane, and haze are still in motion. That sentence contains a scale no single human life can hold. A child born near Pluto's last perihelion would not live to its aphelion. Several generations will pass before the dwarf planet returns to the same point in its orbit. Yet each occultation, spectrum, and archived image adds a few minutes or years to a continuous account. There is a profound humility in that arrangement. Science does not need to witness the complete cycle before it can understand parts of the mechanism. It does need to mark where observation ends and modeling begins. It needs to preserve uncertainty long enough for future evidence to matter. Pluto offers a world built from those careful distinctions. The atmosphere is mostly nitrogen, but not like Earth's. The mountains are water ice, but not like terrestrial glaciers. The bright summit caps resemble snow, but they form through another route. The blue haze resembles the sky, but its particles and pressure belong to another regime. Similarity opens the door. Precision carries us through it. From the surface of Sputnik Planitia, the sun would look like a brilliant star. Its light would be faint by Earth standards and decisive by Pluto's. A slight change in that energy would determine how many nitrogen molecules join the air. A basin hundreds of miles wide would exchange material with a sky extending hundreds of miles high. Charon would hold its place above one hemisphere. The smaller moons would continue their complicated spins. Neptune would remain safely phased by resonance. Far beyond, Arrokoth would turn as two ancient lobes joined together. Between them would be almost all empty space. The emptiness does not erase connection. Sunlight connects the surface to the atmosphere. Gravity connects Pluto to Charon. Resonance connects Pluto's orbit to Neptune. Shared formation connects the dwarf planet to the Kuiper belt. Observation connects one human generation to the next. Pluto was once a moving point between fixed stars. Then it became a measured orbit, a moon-bearing world, a stellar shadow with air, and finally a landscape beneath a blue rim. Each transformation came from seeing the same object with a new method. The next transformation may come slowly. A pressure decline measured across decades. A new frost map from a future telescope. An orbiter returning through the haze. A second close image showing what moved after 2015. Consider the scale from the viewpoint of one patch of frost. Sunlight arrives at a slightly steeper angle as Pluto advances. A few nitrogen molecules gain enough energy to leave the crystal. Each joins a gas so thin that collisions are separated by distances unimaginable in Earth's lower air. The molecules spread, exchange energy, and some reach terrain where the equilibrium favors solid ice again. No single departure changes the landscape. Trillions upon trillions make an atmosphere. Now consider the same process from the viewpoint of a human archive. One occultation produces a light curve. One spectrum records a methane band. One spacecraft image fixes the position of a frost boundary. Each observation is slight compared with a complete Pluto year. Joined across generations, they begin to reveal the climate. The parallel is exact enough to matter. A large pattern can be assembled from small transfers when nothing needs to finish at once. Molecules build pressure. Measurements build understanding. The result depends on continuity. Pluto's long year also changes the meaning of patience. Waiting does not mean ignoring the world until the orbit is complete. It means extracting every reliable constraint from the portion available now, then leaving the record clear for the next observer. The planetarium of one century becomes the baseline of another. You live on a world where seasons return within a year and weather can change before a day ends. Pluto offers the same underlying connection among sunlight, matter, and motion, stretched until the familiar signals become almost silent. Its frost line is a calendar. Its haze is a chemical clock. Its orbit is a history longer than a life. That difference does not place Pluto beyond understanding. It asks understanding to become cumulative. The cumulative view reaches backward as well as forward. Toomba could not know that the faint point on his plate held a blue haze. The scientists who detected the atmosphere in 1988 could not yet see the basin supplying much of its nitrogen. The New Horizons team planned an encounter before anyone had photographed the exact terrain their instruments would cross. Each stage depended on questions left by the stage before it. The same sequence will continue. A future observer may read the 2015 pressure and haze measurements as the early point on a curve whose later shape has become obvious. A future spacecraft may regard the encounter hemisphere as a historical map, valuable precisely because the frost has moved. What is incomplete now can become indispensable later. Pluto makes that possibility visible without hurry. Its climate does not pause while humans decide how to measure it. Nitrogen continues crossing the boundary between solid and gas. Haze particles continue settling. The orbit carries the dwarf planet farther through its season. Knowledge advances by returning to the same distant light with better instruments and a longer memory. Until then, the weather continues on its own clock. Weather and climate meet here at an unfamiliar boundary. Weather is the state and motion of the atmosphere now. Its pressure, wind, haze, and exchange with frost. Climate is the pattern those states trace through a long orbit. New Horizons measured a moment. Occultations extend the sequence. Models propose the full curve. The difference prevents one image from carrying too much meaning. A bright northern cap is not proof of every future season. A haze layer seen in July 2015 is not a permanent band. A modeled wind is not a direct gust measurement. The world is dynamic, and the evidence must remain dated. That dating also makes the present valuable. The 2015 flyby occurred near 33 astronomical units during northern summer, not at a timeless average Pluto. The pressure, illumination, and volatile distribution belong to that orbital state. A later mission would encounter another expression of the same system. There may be a day when two global maps can be placed side by side. Scientists could measure which frost boundaries withdrew, which pits enlarged, whether dune-like ridges migrated, and how haze brightness changed. Even a small difference would connect the equations to visible motion. Until such a comparison exists, restraint is part of seeing. The weather is real. The specific forecast remains a range. Pluto's distance turns that restraint into perspective. Human schedules favor immediate answers, but the dwarf planet offers no obligation to finish its experiment within one career. It only continues around the sun. Thin sky. Long year. Moving frost. Distant light. Good night.